Hi everyone, welcome back to the Chem Help ASAP live stream. So tonight I thought we would kind of continue our theme of acids and bases. So for this live stream, we're going to talk about salts that have acidic and basic properties, how you can tell if a salt has acidic and basic properties, how to tell if it's going to be an acidic salt or a basic salt, and what the pH is going to be. And then we will also do calculations. Yes, with equilibrium, so we're still working with equilibrium. So we'll do calculations on how to calculate the pH of a salt in solution. Okay, but as usual, I thought we would start with some definitions, lay a little groundwork. Of course, any questions you have, just throw them in the chat. And okay, OG Benchmarks, I was going to ask, how is the audio? Is the audio okay? Or is it a little bit too hot? Because I feel like I turned it up last week. So I just want to make sure everything's all right. Okay, so let's go ahead and start. And of course, we'll start with our definitions. So what I've got here is, actually, this is kind of everything at once. Let me switch over to, well, okay, let's maybe identify our conjugate acid-base pairs. And then I will come back to some of these other tables as well. So I don't want to actually go over the calculating the pH of salts quite yet. But I do want to talk about predicting if a salt. So this one, let's first just identify conjugate pairs. Okay, so sorry, I think I meant to pull that first slide out, actually. All right, so to identify acidic and basic properties of salts, the first thing you need to understand is what a conjugate pair is and how it works and what those relationships are. So I've given a couple of compounds right here. And we are going to put these in aqueous solution, and then we're going to see what conjugate pairs come out of this. So again, taking our hydrochloric acid, when we put it in water. Now remember, this is a strong acid, so I only have the arrow to the right. So that was done on purpose. And here is our balanced chemical equation for hydrochloric acid and water. So what I want to do first is just identify the conjugate pairs. Now, when you have an acid or a base in water, you're going to have two conjugate pairs. So you're going to have one acid paired with its conjugate base and a base paired with its conjugate acid. So let's start with the easy one. Hydrochloric acid is an acid, as the name says. But why is it an acid? Again, if you remember your definition of Bronsted-Lowry, an acid is something that is going to donate a proton. So for hydrochloric acid, this is the proton that it donates. Now, where does it donate it? It donates it to water, so you get the hydronium ion. Okay, so once hydrochloric acid has donated its proton, what is left? Well, once the H here is gone, we only have the Cl. So this is the chloride anion. So this is the conjugate base of hydrochloric acid. All right, so I like to kind of put brackets around here. So hydrochloric acid is the acid. Once it donates its proton, then what's left over is the conjugate base. So this is an acid-base conjugate pair. Okay, let's identify the other conjugate pair. So remember how we said that hydrochloric acid donates a proton. That's what makes it an acid. So what is true about a base? A base accepts a proton. So hydrochloric acid is donating a proton. What species is it donating a proton to? It's donating it to water. So in this equation, water is acting as a base. It is going to accept that proton. So when it accepts that proton, it's no longer H2, but it's H3. And of course, we get a positive charge with this as well. So H3O plus is the conjugate acid of water. And again, let's put brackets here. Again, so when you're doing these acid-base conjugate pairs, you're going to be looking for two pairs of acid-base. The only exception is, and I'll just throw this out here, is if you write the dissociation of hydrochloric acid like this, because in essence, you have just kind of thrown the proton out here and nothing is accepting it. Nothing is acting as the base to accept it. So this is a case where using the simplified version of hydrochloric acid in aqueous solution is a little less helpful. Okay, so let's go on to HCN, which of course is another acid. Again, I'm putting it in water. Now, this is a weak acid. So notice I'm going to use equilibrium errors here because we have a forward reaction and we also have a reverse reaction. All right, so this is also going to produce hydronium and it's going to produce cyanide. So there we go. All right, so again, just like we did before, I want to identify the conjugate pairs, and I'm going to have two sets of pairs. Well, I like to start with my easiest one. I'm going to start with my acid, my HCN. This is my acid. Again, it's going to donate a proton. It donates this hydrogen right here. Once it donates that proton, what is left? Well, what's left is the cyanide anion. It's right here. And so this is the conjugate base. And you can see I tend to write my equilibrium expressions the same way all the time. I just kind of got into the habit of that, and then it's a little bit easier for me to find those pairs because I'm always writing the hydronium first. Okay, so in this case, again, you have your acid, which is donating a proton. Where is it donating it to? It's donating it to water, so water is accepting that proton. So water is then acting as a base, which means the hydronium is the conjugate acid. So same kind of deal as the equation above. It looks very similar. We just have different acids. We got a strong acid versus a weak acid, but the conjugate pairs are the same. Now this brings up another point, and that is the relative strengths of conjugate pairs. So the rule of thumb is the stronger the acid, so we'll say stronger the acid, the weaker the conjugate base. And this also applies in the other direction. So the stronger the base, the weaker the conjugate acid. So it might be better even to think of the stronger the acid or the base, the weaker the conjugate. So let's take a look back at hydrochloric acid. Hydrochloric acid, of course, we know is a strong acid. This reaction only moves to the right. It does not have a reverse reaction, which means that the chloride anion is not basic enough to take a proton off of anything. It's not going to take a proton off of water. It's not going to take a proton off of anything else. So this is a very, very weak conjugate base. And what we would say is it does not have any acid-base properties because, again, there is no reverse reaction here. The chloride ion cannot put this reaction in reverse to go back and form its conjugate acid, which is hydrochloric acid. Let's contrast that with our weak acid, our HCN. So again, we have our weak acid. It is in equilibrium, which means I have a forward reaction and a reverse reaction. So this is a weaker acid, but it means that this conjugate base is much stronger than chloride, which is just not a base at all. So our cyanide anion can have this reverse reaction happening. So cyanide is a stronger conjugate base, and it actually will act as a base in water. So it will accept a proton. And so then you have a basic solution. So again, this is where we're going to go with our salts. We want to see with our salts what the conjugates are. Okay, make sure there are no questions. We're good. Let's go on to ammonia, and then we'll do water. And then we'll keep on talking about how to calculate the pH of these, or how to, first we're going to do how to identify if it is a salt with acid-base properties, and then we'll do some calculations. All right, so we've got ammonia. Again, I am putting all of these in aqueous solutions. So these are always, always, always in aqueous solutions. I am not going to deal with solutions that are not aqueous because I don't have any Kas or Kbs for those. All right, so ammonia and water. Remember, ammonia is going to accept a proton. So if it's accepting a proton, that means it's acting as a base. Now, when it accepts that proton, it's no longer NH3, but NH4, of course, with a positive charge there. It becomes the ammonium cation. So here is the conjugate acid for ammonia. And again, I'll draw my brackets there. So you probably know where I'm going with this. What is water doing in this situation here? Oh my goodness, I drew hydronium. See, I got into a habit there. So this is hydroxide. I created a proton. Amazing. So again, you've got water, which up here, water was acting as a base. It was accepting a proton. But in this case, because we have ammonia already accepting the proton, it's already acting as a base. Water is going to act as an acid, which means it donates a proton. So it is giving up a proton. So instead of H2, we now just have a single H, which we write now as OH. I know water is a little bit weird. It would probably be better if we wrote water as HOH, but we don't. We write it as H2O. We just kind of have to live with the rules we've given ourselves. Okay, so this is hydroxide is the conjugate base of water. And again, I'll draw my little brackets right here. All right, so the same rule applies. We have a weak base, which means we have a conjugate acid that can act as an acid because ammonium ion will take the reverse reaction, will make the reverse reaction happen here. Okay, so the last thing I want to talk about is water, and this is the autoionization of water, which you might have heard of that. Actually, I'm going to come over here. So this means you have water reacting with itself. That's what autoionization means. It's reacting with itself. And we get the hydronium ion and the hydroxide anion. Okay, so this is what is always going on in water, even absolutely pure water. This is where our Kw comes from. Now, it's in very small amounts. The concentration of hydronium and hydroxide in pure water are the same. They're 1 × 10⁻⁷. That gives us a pH of 7. Remember, pH is a negative logarithmic scale. Okay, so with our water, because these are identical, it doesn't matter which one we label the acid or the base. We just have to make sure we match it up with its conjugate pair. So let's label this one as the base and this one as the acid. Of course, you can reverse it. That's fine. So if this water molecule is the base, that means it is accepting a proton. So again, instead of being H2O, it now becomes H3O. So it has accepted a proton. So this is its conjugate-ish acid. I'm kind of running out of space there. So here is one pair, which means that this water molecule is acting as the acid. So it is donating the proton. So that means hydroxide is your conjugate base. Okay, so here is our second acid-base pair. Now, when we're talking about aqueous solutions, hydronium cation, hydroxide anion, these are the strongest acids/bases that you can have in aqueous solution. So this is why in aqueous solution we talk about hydrochloric and hydrobromic acids being strong acids. They're both strong acids. And in aqueous solutions, it's very difficult to compare the two to say which one is stronger. You have to go to another solvent to actually figure out which one is stronger. That brings in the leveling effect, which we are not going to get into right now. But just to say, your conjugate acid and your conjugate base here, those are your strongest acids and bases in water. And of course, this is what we use to calculate our pH and our pOH. Okay, so that is how you identify conjugate pairs and just straight up weak acids, weak bases, strong bases, and of course, water. Okay, now we're going to do some predicting of salts. So this is where we're going to take a salt and we're going to predict, is this salt just going to be neutral? We can just throw the salt in water and the pH isn't going to change. It's still going to be a pH of 7. Or is this going to make the solution acidic or basic? So we're not actually calculating now. We're just trying to figure out if it's going to make the solution acidic or basic. So I thought we would take the most classic salt, our sodium chloride, and see if we add that to water, are we going to make the water either acidic or basic? Okay, so our first step you can see I wrote it here, is we're going to dissociate the salt into its cation and its anion. So we want to see what the salt is made of. So I'm going to take my sodium chloride and I'm going to break it up into my ions. So it's sodium cation and chloride anion. Okay, so from these ions, we want to identify the parent acid or base of each ion. So what I'm looking for is these are conjugates, or they should be related to conjugates. So what are they related to? Well, sodium is going to come from sodium hydroxide. So sodium hydroxide is going to give us our sodium cation. All right, so notice what's going on here. Sodium hydroxide is a strong base, which means we only have the right reaction. So we're only moving to the right, which means that sodium is not going to be able to force that reaction back. So this cation is such a weak acid, it has no acidic basic properties. So we'll say no acid base properties. Okay, so what we're looking for here is we're looking for either a weak acid or a weak base for our conjugates. All right, so let's take the chloride ion. We just saw this one. That is, of course, hydrochloric acid and water. This also is right hand only. So this is only moving in the forward direction, which means that chloride is not going to take this in the reverse. So again, it also has no acidic or basic properties. So what we've got is we've got two ions here who are conjugates, but they're still really just spectator ions because they're coming from strong acids and strong bases that only have, especially when you write it this way, the forward reaction. So you would never write this as a reverse reaction because it was not going to go that way. It only moves in the forward direction. So when you put sodium chloride in water, because it has no acid-base properties, your pH is going to be 7. So your pH equals 7. Now this is what is summarized in this very first, oops, I meant to use my laser pointer there. This is what is summarized in the very first row here. So if your cation is coming from a strong base, i.e. it's coming from sodium hydroxide, it doesn't have any acid-base properties. If your anion is coming from a strong acid, like here, it also has no acid-base properties, and your pH is going to remain neutral. Your pH is going to remain 7. Okay, so let's do a different salt. So don't worry now, when you're putting salt, like, you know, in your pasta water, you're not changing the pH. You're going to be changing the boiling point though, but you're not going to be changing the pH. Okay, so we have ammonium bromide. So we're going to do the same thing. I'm going to dissociate the salt into the cation and the anion so that I can see kind of everything broken down first. So I have the ammonium cation and the bromide anion. All right. So now we're going to go back and we're going to identify the parent acid base of each ion. So again, we're saying, is this a conjugate of either a weak acid or a weak base? Well, let's try to figure out if it is or not. So if I look at my ammonium and I think, all right, could that be a conjugate of something? Then yes, it can be a conjugate of something. It can be a conjugate of ammonia. And ammonia, of course, is a weak base. So yes, the ammonium cation can run this reaction in the reverse. So ammonium does have acid-base properties. And specifically, it is going to act as an acid because it's going to be willing to donate a property. So we'll say acidic properties there. All right, so let's go to the bromide because we haven't finished with both of our ions here. So again, I'm going bromide. This is very much like chloride. Your halogens are all going to come from the same kind of acid. This is going to come from hydrobromic acid. And it looks very similar to hydrochloric acid. It is a strong acid. So again, this only moves in the right-hand direction, which means your bromide anion does not have any basic properties. It cannot make this reaction run in reverse. So we'll say no acid-base properties. Okay. All right, so at this point, we only have one ion that has acid-base properties, and that is our ammonium cation. So now what we're going to do is, so we're doing our step 4 at this point. So we're going to look at our table, and we're seeing our cation from a strong base. No, that doesn't work because our cation came from a weak base. Okay, so skip to the next row. Our cation from a weak base. Okay, this is sounding like our situation. So cation is a weak acid. Yes, all right. But what about our anion? Is our anion from a strong acid? Yep, bromide is coming from hydrobromic acid, which is a strong acid. So this is the row we want, which means that our anion has no acid-base properties, which again we set up here. So like everything is coming together. So this means we are going to have an acidic solution. Our pH is going to be less than 7. Again, we are going to calculate this, but just not quite now. So this is an acidic solution, and our pH is going to be less than 7, which makes sense, right? Because we just identified an acid that we have in the solution. Now it's going to be weakly acidic, but it is going to be acidic. Okay, make sure there are no questions. No questions. Okay, let's go on to our next salt. So we have potassium nitrite, and we're going to do the same thing. So let's dissociate it. So potassium nitrite, we're going to have the potassium cation and the nitrite anion. Again, we're going to go and figure out where, if these are conjugates, where they're coming from. So potassium is very much like sodium, and this is going to be true for all of your group 1 elements. They're all going to be coming from hydroxides. So if we have potassium hydroxide, this gives us our potassium cation and our hydroxide anion. All right, again, notice this is a strong base, so it only moves in the forward direction. It only moves to the right. So potassium has no acid-base properties because it cannot move this reaction back to the left. Okay, so we'll say no acid-base properties. All right, now let's take a look at our nitrite. So nitrite, again, thinking of it as a conjugate, what acid would it come from? Well, it would come from nitrous acid, which is a weak acid. So this is an equilibrium. Oops, plus. And here is our nitrite, which means nitrite is a strong enough base to run the reverse reaction. So it will act like a base in water. So we'll label this as basic. All right. Okay, so now again, I'm coming to, we've determined if the ions have acid-base properties. Now we're doing number 4 to look at our table and decide which way it's going to run. Okay, so this is cation and anion from strong acid, strong base. No, we don't have that. We have cation from a strong base. Yes, that's true. And anion from a weak acid. Yep. Okay, so we're looking at row number 2 here, which is exactly what we wrote up here. A cation has no acid-base properties. Our anion is a weak base. Yep, which we said. So we are going to have a basic solution for this salt, or I should say this salt will make a basic solution. And so our pH is going to be higher or greater than 7. Okay, so hopefully these are getting a little bit easier. You kind of have to run through them a couple of times. And yes, nitrite and nitrate, it's just a 1 letter, but it makes a big difference whether you've got a strong acid or a weak acid. Nitric acid is strong, but nitrous acid is weak. Okay, so let's do... you know, I feel like with 726, if we have time, I want to come back to this because I really want to get to polyprotic acids if we can do that. So I am going to skip over this one initially. Just suffice to say, we're going to have the ammonium cation and the fluoride anion. This is, they're conjugates of both a weak acid and a weak base. We're going to be looking at this one right here. Now, some classes will talk about these and some classes will just stick to these first 3 rows, which is why I kind of feel like let's skip it for now, and if we have time, we'll come back to it. Okay, because I really want to get to these calculations, and also I would love to be able to get to talk about at least the polyprotic acids just a little bit. Okay, so now we're actually into making our calculations. So we're going to calculate the pH of the solution of ammonium bromide. The concentration of the solution is 0.1 molar, and the Kb of ammonia is 1.8 times 10 to the negative 5th. Okay, so You probably recognize the salt because we talked about it. Not this one. Not this one. We talked about it right here. Okay, so we've already determined that this is going to be an acidic solution because we've got a weak acid in solution. So now we're actually going to practice calculating what the pH is, and let's see what's going on with it. Okay, so I'm still just going to take my original salt here. Oh, I don't want to write under my video feed there. And break it up. Now we have already done this, but again, when you're starting this problem from scratch, you're going to still want to be able to break this up into a cation and an anion. Now we've already recognized that this ammonium cation is what is driving our acidic and basic properties. So what is going on then with ammonium in aqueous solution? Okay, we know it's going to be in equilibrium because this is going to be acting weakly acidic or weakly basic. Okay, we already decided this, but think about the ammonium cation. Is it going to donate a proton or is it going to accept a proton? Well, it actually already has an extra proton because when you think about ammonia, right, that's NH3. So it's already accepted a proton. So this is going to act as an acid and it's going to donate a proton. That means we have ammonia and hydronium. All right, so this is the equilibrium that is going on in solution. So we have the ammonium cation. Again, it's making a little bit of hydronium. We just don't know how much yet. So now that we've written out our balanced chemical equation, let's go ahead and calculate let's just write down what our Ka is. So this is our equilibrium constant. So remember, it's going to be products over reactants. Sorry, this is ammonia times hydronium. And remember, when we have Kas, that concentration of water is folded into the value for Ka. So we don't have to include water in the denominator here. All right, so this is all well and good. So we have at least we have an expression for Ka. We've got a balanced chemical equation, but I don't have a value for this Ka. So, but I have a value for the Kb of ammonia. Well, remember that ammonium and ammonia is a conjugate pair. That means that I can use the Kb of ammonia to figure out numerically what the value of Ka is. And these are connected by the equilibrium constant for water. These are connected by Kw. So remember, Kw is equal to Ka times Kb for conjugate pairs. Only for conjugate pairs. So you can't use this to say, calculate the Ka for, nitrous acid in this case. It only works for conjugate pairs. This B is really bothering me. That is a B right there. All right, so I know my Kb. It's 1.8 times 10 to the negative 5th. So this is 1 times 10 to the negative 14th. It's equal to Ka times 1.8 times 10 to the negative 5th. This gives me a Ka of 5.6 times 10 to the negative 10th. Okay, so now we have a value for Ka. We've got our expression for Ka. We've got our balanced chemical equation. Now we're going to deal with our equilibrium. So now is when we're going to use our ICE table or RICE table, if you will. Okay, so I'm going to do this on the left-hand side. So I'm going to rewrite my balanced chemical equation. Plus water gives ammonia and the hydronium cation. All right, so ICE. I is initial. How much are we starting with initially? Well, we're starting with 0.1 molar, and we're starting with no ammonia and no hydronium. All right, consumed or change. How much is it going to change? We don't know, so we call that X. So we're going to use up some of our ammonium cation. We're going to create some ammonia, and we're going to create some hydronium. Now we just add down the column. So this is 0.10 minus x. This is x, and this is x. So now we just plug into our expression for Ka here. So Ka is equal to, again, going back here, it's my products, which are x and x. So x and x, divided by my reactant, which again is my ammonium right here, 0.10 minus x. And of course, this equals our value for Ka, which we calculated right here, 5.6 times 10 to the negative 10th. All right. I've got a quadratic here. X times x is x squared. What I'd really like to do, of course, is drop this minus x right here, because then I can solve for x squared by just doing a square root. But of course, we have to test and see if we can drop that, that minus x. So I'm going to do what I call the 500 test. So this is my concentration of my acid, my initial concentration of acid over Ka. And this should be greater than 500. So if I put these values in, and this is 5.6 times 10 to the negative 10th, should be greater than 500. All right, so come back up here. So if I calculate that, I get 1.8 times 10 to the 8th, which, yes, is definitely bigger than 500. Which is not surprising, because remember, your Ka here is 10 to the negative 10th. So we can feel very comfortable dropping this minus x, which means I need another page. Okay, so going back, I'm just going to rewrite my Ka expression here. So this is 5.6 times 10 to the negative 10th. This now equals x squared over 0.10. Again, so I'm just pulling from right here. I still have my x squared on top, but I've dropped that minus x in the denominator. So now I can just solve for x using a square root. And this is 7.5 times 10 to the negative 6. Okay, so that is what my value for x is. But just like when you're doing any equilibrium problem, you're working through a lot of math, it's easy to forget what is x, what does x mean. So go back to your ICE table. Remember, x was your change. And in your equilibrium row, notice what x is. It's your concentration of your hydronium ion. So this equals my concentration of my hydronium ion. This is really good news, right? Because I'm trying to calculate pH. So this is negative log of hydronium, which we now know. So this is negative log of 7.5 times 10 to the negative 6, which gives me a pH of 5.12. Okay, does that make sense with what we predicted in the first place? Well, yeah, we predicted it to be an acidic salt. And you can see, yes, our pH is less than 7. It's not hugely less than 7. It's still a very weak acid, but it does make our solution weakly acidic. So this is how you work through the math of all of these. Okay, let's go on to another calculation because we're doing okay on time. Okay, so this one we've got potassium nitrite, which again we have seen, we have talked about, here. So we talked about it here. Again, so we've determined actually already that we have a weak base in this solution. So now we're going to actually do a calculation and figure out what the pH is once we're given a concentration here. Okay, so we have the concentration of our solution is 0.25 molar, and we have the Ka of nitrous acid is 4 times 10 to the negative 4. Now, one thing I will say is you might, instead of being given Kas in the problem itself, you might be given a table of Kas. So make sure that once you identify, like in this case, my nitrite, I go back to my nitrous acid and use that Ka. So that will make the problem a little bit more difficult if you're just given a table, because you have to make sure that you're using the Ka of the correct conjugate acid. Okay, but that aside, I am going to rewrite my dissociation of my salt. So this gives me the potassium cation and the nitrite anion. So again, remember the potassium cation is just a spectator ion. It doesn't do anything. It's not going to change the acid-base properties of the solution. We're really just focused on the nitrite because we know that is a conjugate base of a weak acid. So just like we did before, what is going on with nitrite in aqueous solution? Well, it's a base, so it's going to accept a proton, which means it goes back to nitrous acid, and then we have hydroxide left over from the water. So remember, it's taking a proton from your water, so instead of H2O, this becomes OH. That's a connection that students sometimes have a hard time making, and I think it's because we change the order of the hydrogen and the oxygen. We don't write it HO, we write it OH, but it is the same thing. Okay, so let's get, just like before, let's get an expression. Let's get a Kb expression for this conjugate base. So this is going to be a Kb. Again, it's just products over reactants. There's hydroxide, and let's put it over our nitrite anion, sorry, not cation. And then how do we get the value for this Kb? Well, we need to use its conjugate acid, which we have. So remembering that Kw is equal to Ka times Kb for any conjugate pair. We've got 1 times 10 to the negative 14th equals our value for Ka. Again, if our nitric acid was given to us in the problem, 10 to the negative 4th times Kb. So our value for Kb is 2.5 times 10 to the negative 11th. Excuse me. All right, so now we have an expression for Kb. We've got a value for Kb, which means it is time now to go to our ICE table and calculate our equilibrium concentrations. So again, I'm going to do this in the lower left. I'm just going to rewrite my balanced chemical equation here. Oops, let me give myself space to write ice. So we have nitrite in water. It is accepting a proton and hydroxide. Great. And now we have IC, oops, that's a C. ICE. So initial, what is our initial concentration of our nitrite? It is 0.25 molar. Ooh, the other thing that I should probably point out, because I've just been kind of skimming over this, assuming that you guys are understanding the stoichiometry behind this. Going back to our balanced chemical equation for the salt dissolving in water, notice that we have a 1-to-1 ratio of our salt and our anions, which means our concentrations here are equal. So when we've got a 1-to-1 ratio, this is where I'm getting the 0.25 here. If you had like a 1-to-2 or a 3-to-2 or something else, then you would have to take that stoichiometry into account. But these are all 1-to-1 ratios, which is why my concentration of nitrite is 0.25. So there's a question. 10 a la minus 1. I am not sure, where that is coming from. Are you talking about the calculation of Kb here? Maybe that this is actually a negative 11. That's what's not super clear. Let me just, I can make this, write this a little bit more clearly. That is 10 to the negative 11th. Okay, so back to our row of initial concentrations. Nitrite is 0.25. These quantities are both 0. So again, what is the change or what is consumed? We don't know. We're going to call it X. These are all 1-to-1 ratios. And now again, we just add down the column to get our equilibrium concentrations, which I know feels weird because we have all these X's, but we're getting ready to find the value for X. All right, so here are our equilibrium concentrations, even though we don't have numbers for them yet. Let's go back to our expression for Kb. Okay, so remember it's right here. So I'm taking my concentration of nitrous acid, my concentration of hydroxide, both of which are X. So that is X times X. And I'm putting it over my concentration of nitrite, which is right here. It's this expression, 0.25 minus X. And of course, this equals my value right here, my 2.5 times 10 to the negative 11th. Now, at this point, I could calculate my 500 rule, but you can see that, this is 10 to the negative 11th. And remember back here when we calculated our 500 rule, we had 10 to the negative 10th, and this ended up being huge. It was much bigger than 500. So we're just going to skip that step because we know it's going to be bigger than 500, so we don't have to mess with it. So at this point, I'm going to go to another page just so I've got space. All right, I've got my KB, which is 2.5 times 10 to the negative 11th. And this is now going to equal x squared over 0.25. So what I've done is I have taken this expression right here. I've just made that x squared because it's x times x. And then I have dropped this minus x because we can drop that minus x. It's totally within error for that. Now it's much easier to calculate x squared. I can do that with just a simple square root. So I get a value of x of 2.5 times 10 to the negative 6. Okay, as always, it's great to get a value here, but what does x mean? We need to go back to our ICE table and see what x means. So x is, okay, our concentration of nitrous, but really I'm focused on here. This is our concentration of hydroxide. Okay, so our hydroxide is going to connect us in with pH. But first, what I like to do is to calculate pOH. So pOH is equal to negative log of hydroxide, which we know. This is 2.5 times 10 to the negative 6. So our pOH is 5.6. So hopefully at this point, if you forgot that you were actually calculating pOH and you thought you were calculating pH, hopefully some bells would be going off here, because if you have a pH of 5.6, that means you have an acidic solution. This should be a basic solution, right? Because what is working here? We've got a conjugate base working in solution. So we should have a pH above 7. So it's always nice, again, to use those little checks, because this saying that this is your pH is just such a common error in students' papers, because you kind of get rolling and you get used to always calculating pH from X, but remember, sometimes you're actually calculating pOH from X. Okay, so then we use this expression, 14 equals pH plus pOH, which equals to pH plus 5.60, which means that our pH is 8.40. And this makes more sense. So this is a basic pH. It's greater than 7, which makes sense. Again, remember, we've got a conjugate base in solution here, and here's a conjugate base here. It's acting as a base. It's accepting protons. It's making hydroxide, so we should have a basic solution. Okay, so we've got a little bit of time here, so I'm going to keep on rolling. All right, so let's talk about polyprotic acids. I don't know if we're going to get back to that that salt with the weak acid and weak base. Okay, but let's talk about polyprotic ions, because I'd really like to do at least one calculation with polyprotic. So a polyprotic means many protons. So these are acids that can donate more than one proton. So usually, or so far, we have dealt with, at least in these live streams, we've dealt with monoprotic acids, meaning they only have one proton. But these are going to be acids that can donate more than one proton. So we're starting with sulfuric, the classic. It has 2 protons to donate, and it is going to donate them stepwise. So let's write the balanced chemical equations for this stepwise donation of these protons. Okay, so the first proton, again, we're always in aqueous solution, so plus water here. We are going to get HSO4, and we are going to get the hydronium cation. Okay, so this is the first step. So I've gone from H2 to just H here. I've donated 1 proton. Again, this makes this balanced chemical equation, all the stoichiometric coefficients are 1. This is 1 to 1 to 1, which makes things really easy mathematically, as hopefully we'll see in a little while. We call this Ka1. Now, For sulfuric acid, you'll notice I did not draw equilibrium arrows. That was on purpose. So this, your first proton in sulfuric, this is a strong acid. So what you usually see for Ka1 is it'll say just large. Sometimes you'll see where it'll say strong, but it says large, meaning there is no value for Ka, because remember we talked about this before, you don't have any more H2SO4 in solution. So if you're thinking about your equilibrium expression, remember we divide by reactants. Well, this goes to 0 and you can't divide by 0. Okay, so our Ka1 here is large because our first step is a strong step. But sulfuric acid has 2 protons to donate. So let's see what happens when that second proton is donated. So this time we're talking about HSO4, not H2SO4. We're still in water. And now what's left is our sulfate anion. But we get another mole of hydronium. So again, you can see that this proton has been donated. Now we just have sulfate. We don't have any more hydrogens left, and we have formed more hydronium. We call this Ka2, and this has a value of 1.2 times 10 to the negative second. Oops, that is a 10 there, 10 to the negative second. Okay, so I messed up, right? Because I drew this as just a right-hand arrow. But once we have an equilibrium value, we are in equilibrium. So that is a way you can tell if you're unsure, should I just draw the right-hand arrow? Should I draw it in equilibrium? If you have a value, if you have a K value, whether this is a Ka or a Kb or any kind of Keq or a Kc, that means it is in equilibrium. Remember up here where it was just large and you didn't have a value, that means it's a strong step. You only have the forward reaction. You do not have the reverse reaction. Okay, let's do the same thing, but let's do it for carbonic acid. Again, this has 2 protons to donate, and we're going to donate them stepwise. So we start with our carbonic acid, and this is going to be in equilibrium, and we just donate 1 proton so that everything is 1-to-1 in our balanced chemical equation. And we do have a value for Ka1. This is 4.3 times 10 to the negative 7. So you can see carbonic acid, even in the first step, is not very strong. This is a pretty weak acid. However, it still does act as an acid because it's going to donate a proton. Now let's see what happens when we donate the second proton. So now we're starting with hydrogen carbonate here. Again, we're still in aqueous solutions. And we're going to be left with just carbonate plus some more hydronium here. Okay, this is an equilibrium. Now we call this Ka2 because this is the second proton that is donated, and it has a value of 4.8 times 10 to the negative 11th. So this is the trend with polyprotic acids. Your first step is always going to be your strongest step. It's going to have the largest Ka value. So you can see this is not a very big value, but it is definitely bigger than 10 to the negative 11. So your first step is still the strongest step, but in the case of carbonic acid, both of these are in equilibrium because they're both weak acids. Okay, no questions. Let's go on to phosphoric acid. Okay, so phosphoric acid, this is a triprotic acid because H3. So it has 3 protons to donate, which means we can write 3 steps for these donations. So we'll start with just our H3PO4, again in water. And this is in equilibrium. Okay, so we've donated 1, oops, not H2O, H3O. Donated that proton. This again is Ka1. This is the first proton that has been donated. This has a value of 7.5 times 10 to the negative third. Okay, so we're definitely better than carbonic acid, right? But we're still definitely weaker than the second step of sulfuric acid. Okay, so now let's take our take another proton off. So now I'm going to start with H2PO4. Don't forget the charge. It's still in water. It's still in equilibrium, so now we just have HPO4. So again, I've gone from H2 to just a single H, and now this has a -2 charge. And we've got more hydronium. Okay, so this is Ka2. This is your second proton. This is 6.2 times 10 to the -8th. And so you can see, again, we've gone from 10 to the -3rd to 10 to the -8, so we've gone to a weaker step here, just like we expected. But phosphoric acid, we've got one more proton here that we can donate. So we can write the third step of phosphoric acid, again, in aqueous solution. It's in equilibrium. Now we just have the phosphate anion left, but we formed another mole of the hydronium. And so we have Ka3, and you can imagine this is weaker than our second step, times 10 to the -13th. So generally what happens with these polyprotic acids is when you are calculating pH of these acids in solutions, usually, although you have to run through the calculation, usually your first step here is going to dominate, and your second step, or in this case, your second and third step, just contribute so little to the situation, or so little hydronium molecules that it does not change the pH. Now, one of the major exceptions here is sulfuric acid, and this one kind of sits on the line. So sometimes you do need to take into account the second step, and sometimes you don't need to take into account the second step, and this all depends on concentration. So the higher your concentration of sulfuric acid, the more you need to worry about just the first step and not the second step. But once your concentrations start to get a little bit smaller, then your second step is going to start having a significant contribution to your pH, and it will lower your pH. So this is the calculation that I would like to go through here. And so I've got it up. All right, so what I want to know is, what is the pH of a solution of 0.1 molar of sulfuric acid? And you can see here, again, I'm given the Ka, Ka2. So once you see that 2 there, you know you're talking about your second step right there. So this is why we label it Ka1 and Ka2. Again, 1.2 times 10 to the -2nd. Okay, so let's do this calculation, and I will just go ahead and do the spoiler. In this case, our concentration is small enough that our second step is going to make a difference, and we're going to need to take that into account. Okay, but let's talk about the first step. Remember, the first step is the strong step. You only have the forward reaction. So that's the easy one. So we start with H2SO4, of course, and water. It only goes to the right. We form hydronium and HSO4. Okay, great, great, great. We know that whatever our concentration of sulfuric acid is also equal to our concentration of hydronium, because again, stoichiometrically, we've got a 1-to-1 ratio here. And that means our concentration of hydronium is 0.100 molar. Okay, that's great. I'm not going to calculate pH yet because we're not ready for it yet. This is the place where a lot of students would just stop and they just wouldn't take into account your second step. But like I said, I've spoiled it. In this case, we do need to take into account our second step. So what is our second step? We're going to take our HSO4. Again, it's in water. It's in equilibrium. It is also making hydronium ions. So we're going to use this because it's in equilibrium. We're going to use this again to make an ice table. So like you see these ice tables just over and over and over and over again. That's because whenever you're dealing with equilibrium, you're going to go back to these ice tables. And when you're dealing with a weak acid or a weak base, you go back to the ice table, and you go back to the ice table, and you go back to the ice table. All right, so our initial concentration here is 0.100 molar. Again, we don't mess with water. Okay, but we've got a little bit of a difference here because we do have hydronium in solution already, right, from our first step. So you can also think of this as a common ion problem as well. So the value for how much we're starting with hydronium initially is not 0, and we're used to always seeing the products be 0. But in this case, our concentration of hydronium at the start is also 0.1. Now our sulfate is 0. That's normal. That goes to 0. So just be aware, again, when you're doing these polyprotic acids, that whatever step came previous is going to contribute to your hydronium concentration there. Okay, so now C for change. This is going to be minus X, this is still X, and this is still X. So this equilibrium is going to drive right because we have no sulfate anion. So if you remember Le Chatelier, it wants to create at least some sulfate. So this is going to drive the reaction to the right initially to create some of that sulfate, and then it'll form an equilibrium concentration. When you do other equilibrium problems, it can be more difficult to determine if the equilibrium is going to shift left or right, but these are a little bit easier because, again, when you have a value for 0, it's going to shift towards that equilibrium concentration. Okay, so now I'm just adding down the columns. So this looks kind of like we're used to, but remember your hydronium looks like that, and then this is just X. So now we have multiple quantities to deal with, right? Okay, so Ka is equal to our products over reactants. So we're going to have a lot of X's here. And this is over HSO4. Okay, so just plugging in our equilibrium concentrations, we have 0.100 plus X. Sulfate is just X, and then this is over 0.100 minus X. Okay, all right, so we'll just do a quick test calculation. I can tell you we're going to have to use quadratic. So if we take HA over our Ka and say, is that greater than 500, we have 0.1 over our Ka, which is 1.2 times 10 to the negative second. So we're hoping that's greater than 100, but this is actually 8.3. So this quantity is not right. So that's a big fat no, which means we need to use quadratic. Okay, so here is where you can get a little bit lost in the math. So just be careful and take your time. Okay, so I'm going to take this and I'm going to distribute this X, 0.100X plus X squared. This is still over my same quantity here. How are we doing on time? No, we're totally running out of time. Okay, so mathematically what we do is we're going to take this denominator and we're going to bring it over to the left, and then we're going to combine like terms. So I have actually already done this part, so I'll show you what the quadratic looks like. Now remember, when you're setting up an equation, to be able to use the quadratic equation, you want to set it equal to 0. So this expression simplifies to 0 equals x squared plus 0.112x minus 1.2 times 10 to the negative third. Okay, so this is our quadratic. So remember, you have your, well, our value for A is 1. You have your value for A, for B, and for C. Don't forget that negative right there. This is really handy if you have the quadratic equation programmed into your calculator, which I definitely recommend here so you don't have to do this out by hand. Okay, so using your calculator, of course, you get two values for X. We get 0.009848 or negative 0.1218. Okay, so when you're deciding between your two values of X, and usually in the case of using quadratics for equilibrium, you'll get one positive value and one negative value. Remember, you can't have a concentration that is negative. That does not exist. So it makes it very easy to determine that this is not the correct root, or I'll write no right there. So don't use the negative value. Go with the positive value. So this is your value of X. Okay, we're almost there, I promise. Remember, your value for X is your concentration of your hydronium ion. But we need to be very careful here because your concentration of hydronium, if you go back to your ICE table, remember, is 0.1 plus X. It's not just X. Again, we get used to just using X and plugging into our pH equation, but remember, it is 0.1 plus X. So this is 0.100 plus 0.2. 0.09848. So our concentration of hydronium is equal to 0.109848. Our pH is just our negative log of this value, 109848. So our pH here is 0.96. So it doesn't change it tremendously, but it changes it enough that it is beyond this, experimental error here. So we do need to take it into account. So it is dropping your pH even lower than what you would expect if you just took into account your first step alone. And what you'll find is, again, the smaller the concentration, in this case of sulfuric acid, the more that second step counts towards calculating your pH, because it's going to contribute more percentage-wise than along with the first step. Okay, so I don't see any other questions here, but as always, let me know what you want to see. What are you doing in class? What are you struggling with? What are you getting ready to do in class? Just let me know. I am happy to do anything in the live streams. I just really need to know what you guys want to see, what is going to help you most. So I hope to see you next week, and we'll be doing something else. We'll see what you guys request. Thanks so much. Bye.